So this is the video lecture that's taking place of what would have been class on the 25th, Memorial Day. Hope you guys are having a good one. So we're going to be going over chemical kinetics, reaction rates, instantaneous rates, rate laws, rate orders, and integrated rate laws, and the half-lives that go with those. So very exciting stuff. Because we're not doing this as a class, it's probably going to go a little bit faster. This is not going to be a 40-minute presentation, but at any rate, your book is a very valuable resource in this, and I strongly encourage you to go through it and take a look at it. So chemical kinetics, it's the topic of the week, and basically what we're trying to do is describe the timing of chemical reactions. So some are fast and some are slow. Some reactions go faster if you have more stuff in it. For some reactions, putting more stuff in it doesn't have any effect on the rate of the reaction. But what it does do is it represents a very important branch of chemistry. And so kinetics you can see right here. Oops. Kinetics you can see right here. And let me put the I want yeah, anyway. I wanted to do that, but I'm not going to. Anyway, it represents a very important branch. So kinetics is one of the things that greatly influences equilibrium, as does thermodynamics. So some reactions are driven entirely by kinetics, that is, they happen at a speed that makes sense. Some reactions have kinetics that are so slow that thermodynamics kind of takes over and drives it towards equilibrium. Both of these are major contributors to equilibrium, which is sort of the thesis statement of this entire semester. So this is very much worth paying attention to. So what is a chemical rate? So if you imagine we have this reaction of H2 and I2, and they go to 2HI, the change in concentration of just one of these reactants, let's just pick H2, over time. So at two different times, an initial time and later, so T1 is initial, T2 is later, the concentration of this and the concentration of that are both noted, and then the difference between those two concentrations divided by the difference in the time will give us a rate. And because this is a reactant and it's going away, we put a negative sign there to show that it's disappearing. So its concentration is going down over that time. So this number here will always be less than this number. We're always going to have less than what we started with. So the negative number will, revert this back. Same thing for iodine. And so we can express it the exact same way. But for hydrogen, you notice that negative, HI, that negative sign disappears. And we have a 1/2 here. So 2 moles of HI are made for every 1 mole of H2 and 1 mole of I2 that are consumed. So HI is made as twice as fast because we get 2 molecules of this every time one of each of these molecules disappears. So its rate is multiplied by the reciprocal of this, which becomes 1/2. And that makes its rate equal. So the negative sign also goes away, and the rate at which this stuff disappears is the same rate that this stuff disappears, is the same rate that this stuff appears once the 1/2 is taken into consideration. So we're able to calculate average and instantaneous rates, and these are some really common curves. And so concentration of like H2 is this green line going down, concentration of I2 is this red line, going up is this curved line. And as more and more of this goes away, it's the rate at which it goes away starts to level off, and as more and more of HI forms, the rate at which it forms tends to level off until they would just sort of plateau. And that plateau for us is the equilibrium, which we're going to get to in another chapter. So the instantaneous rate for this. So the average rate is the rate over, a length of time, like a long length of time. The instantaneous rate is the rate at any one instant in that. So what we do is we take the slope of a tangent line that goes through here. So it takes a little bit of calculus to do. Now that's not actually what we end up doing in this class, the calculus of it at least. We recognize that it's there, but we don't use it in the math. We actually greatly simplify the math to some simple algebraic equations. But if this is the concentration curve over time, the slope of a tangent line at any instant in that time is what's known as the instantaneous rate. Okay, and you can think of like an average rate. If you're a runner, your average rate over a 5K or a 3 mile race is, you can calculate that, but you went faster or slower at different points in that race, probably fast at the start and fast at the very end, but not as fast in the middle. So you have an appreciation for average and instantaneous rates. So for a general instantaneous rate for any given reaction, A moles of A, B moles of B goes to make C moles of C and D moles of D, we would write the rate for any one of these to be, negative of 1 over the coefficient times the rate of change of A with respect to time. Same thing for B. Now for C and for D, that negative sign goes away. And then for your book's got this great question, for the reaction A plus 2B goes to C, if the initial rate is 0.1 molar per second, what is the change in concentration of B with respect to time under the same conditions? So there's an actual number that you would get to with this that's based on what we have here, specifically this part, if you want to take a look at it. Now, I'll have a sip of coffee. You should try this problem. It's right out of your text. Just try it. Okay. So the rate of this is 0.1 molar per second, and that is equal to negative 1 over B times the change in concentration of B over time. All I need to do is plug in a 2 for that lowercase b, because that's the only number I have given from this equation. And then I'll go and multiply it through. So negative 2, multiplying both sides by negative 2 gets rid of this sign. So now I've just got delta B over delta T. And negative 2 times this, so it's negative that. So my rate of change of this is negative 0.2 molar per second. All right, and that just tells me, the speed with which this stuff is going away. Now, rates are determined experimentally. There's no way we can look at a chemical reaction and determine that our reaction is fast or slow. So it's done experimentally. One way we can do it is through spectroscopy. That is, we can look at a certain species that absorbs or emits light and watch that change as a reaction occurs. So if it's being consumed or being made, this graph will go down or go up. And another way is looking at how things might happen in the gas phase, so that you can use chromatography, which uses another bit of equipment. But again, the point I want to make is that we're doing this experimentally. We can't just look at a reaction and then tell you something about its rate. And that leads us to a rate law. So here's a basic equation. A goes to products, okay? Don't worry about balance or anything like that. The rate law for this would be a description of what the rate for that is based on the concentration of the stuff that we start with. And they're always written in this form. The rate for something is equal to some constant K, which is what's known as the rate constant. It's a temperature-dependent entity that is unique for every kind of reaction. And that is multiplied by the amount of reactant that we have here raised to some power. This power is an integer in most cases. Not all, but most. And there are 3 common values for this integer, 0, 1, and 2. So if that exponent there is 0, this reaction is referred to as 0th order. And that means that the rate of the reaction has nothing to do with the amount of stuff that's reacting. So any number raised to 0 is 1, so the rate of this would be equal to the rate constant. If that n is equal to 1, it's referred to as first order, which means that the rate is directly proportional to the concentration of A. So if I double A, then I double my rate. If I triple A, I triple my rate. That is what's known as a first order reaction. Now, if n is equal to 2, what that means is that if I double the concentration of A, so like let's say 2A is what goes in here, that means that 2A quantity squared is the rate, which means it's 4 times as fast as it was before. So it's proportional to the square of the concentration of A. And then the next slide is going to walk us through how we can actually get that from experimental data. I'm sorry, the slide after this one. So here is, if we were to plot these concentrations, like the concentration of A over time, for a 0th order reaction, no matter how much A we have, its rate of going away doesn't change, so it keeps going down steadily. For first order, it goes away in a proportional way, but curves in this direction. And then second order, it curves away in this way. And the only way we could know this is through plotting. The rate of concentration for first order, if we're plotting rate on one axis and A on the other, The rate doesn't change at all for 0th order, so it stays the same always. For first order, it's linear with respect to the concentration at A. And then for second order, it curves up at the rate of the square of A. So we get that parabolic sort of looking thing. So what we're going to do is determine the rate law from data. So here's a table of data. And in the first trial, when our initial concentration is 0.1, our initial rate is 0.015. When our concentration is 0.2, our initial rate is 0.06. And when our concentration is 0.4, our initial rate is 0.24. So I'm going to pick any two trials here. It doesn't matter which two. I'm going to pick 2 and 3. I could just as easily have picked 1 and 2. And I'm going to put 3 on top, 2 on the bottom. Again, it doesn't matter. So I could have put 2 on top and 3 on the bottom. But this way I have positive numbers that are larger than 1. So I like it doing it this way. So 0.24 will be my rate for 3 and my rate for 2. So my rate for 3 is whatever the rate is, 0.24 in this case, is equal to some constant k times whatever my concentration is raised to some value of n. And I'm trying to find n. That is my goal here. So I'm going to take this number, I'm going to start plugging things in here. So 0.24 is equal to k times 0.4 times raised to the n. For the second one, it's 0.06 is equal to k times 0.2 raised to the n. Now, when I do this, I can divide these by each other. So 0.24 divided by 0.06 is 4. K divided by k cancels out, so that's 1. 0.4 to the n divided by 0.2 to the n is 2 to the n. And so now I have this expression, 4 equals 2 raised to the n. I think we can all kind of see that n equals 2 here because it's a number we can work out. But to show you how we get there, we take the log of both sides. And the way logs work is that exponent comes down. So log of 4 equals n times the log of 2. N is equal to log of 4 over log of 2. And that comes out to 2. Now, what that means is that my rate law is written like this. For the reaction of A going to products, using this data, I can tell you that the rate law is equal to k times A squared, meaning my rate will go up proportionally as the square of A does. But what is that value of k? Can I figure that out? So the way that we do that is we pick a trial. Pick any trial. Okay, and I'm going to pick here this third trial. There's no reason for me to pick this one over a second or third. It doesn't matter. I just want to pick this one. So the rate is 0.24 molar per second, and that's equal to some constant k, which I'm trying to figure out, times 0.4 squared. So all I need to do is divide both sides by 0.4 squared. And when I do, I get a k that is equal to 1.5 per molar per second. It's important you get the units right on k, because that is, it's part of the answer, so it's something we want to get at. But also realize that the units of k are different depending on the order of the reaction. So if we have a different order of the reaction, units of k will be different, but the rate is always molar per seconds or molar per unit time, which is usually seconds, but can be minutes, days, years, whatever's appropriate. Okay. So the rate law versus the integrated rate law. So what we just did there is we found out what the rate law was based on instantaneous or initial rates. And the rate law is really good because it shows us a relationship between the rate of a reaction and the concentration of its reactant. However, what we'd like to sometimes do is say, okay, at some point after this reaction has started, what is the concentration of stuff that remains? And that's an important thing for us to sort of figure out. So we use an integrated rate law when we want to look at the relationship between concentration and a reactant over time. So the integrated rate law is really helpful for predicting that. So I made 3 videos that show the 0th order, 1st order, and 2nd order way of using these rate laws. And it's calculus that takes us from this expression to this expression. We do not go into that calculus, so do not worry, it's not a prerequisite for the course. And these are the different things here. Now what this does though is this gives us a y equals mx plus b, and again that's described in the other video, way of just plotting these things out so that we can on a linear basis show what the concentration is with respect to time. So here are the equations for them. In a typical class you would actually have to commit these to memory. In this version of the class that's not something that's going to be expected. Now, the final thing that we're going to go into here is something called half-life. And the half-life of a reaction is the amount of time that it takes for the sample something to go down to half of its original concentration. So if I originally started with 4 moles of something, the amount of time it takes me to get down to 2 moles is the half-life, or how long that takes. So at the half-life, or t sub 1/2, that's sort of the way we show that, the concentration at that time t, this is the concentration at some time t, it's going to be equal to our original concentration divided by 2. That's it. So by plugging this quantity, A0 over 2, into these expressions individually, we can get different expressions for half-life. Now that's a powerful thing, because if I know the rate constant K, and the initial concentration, that means at least for a 0th order reaction, I can just calculate the half-time. I don't have to do another experiment. For this one, the amount of the initial concentration doesn't even figure in. If I know the rate constant, I can figure out the half-life. And then for the second order, it does figure in again. So it's a very powerful tool, and this is worked out. It's derived in the other videos that I made for you. So this is a good sort of pausing place for us, because from here we would go on to another sort of aspect of this, which has to do with the values of K and how that changes with temperature. So we'll stop here, and we'll pick up on Wednesday. All right? Take care.